Hello again. In this last part of this lesson on study Stokes in 2 dimensions, I'm going to show you how to write the code or how to adapt the code that we have written so far for the stabilized formulation in the previous part for LBB stable elements. Okay, so before going into the coding part, just a brief recap of what this LBB or sub stability is. Okay, so after we discretize the weak form for the study Stokes equations, okay, so we get this 2 by 2 black matrix with a 0 diagonal at the 2 by 2, okay, at the blot 2 by 2, okay. Now this is called a saddle point problem. Okay, so there is a lot of theory behind it with these saddle point problems. Okay, so we encounter these saddle point problems primarily in optimization, where we want to minimize like a function, some let's say energy, and then there are some constraints. Okay, so we apply those constraints using Lagrange multipliers to enforce them. Okay, to enforce those constraints, we use Lagrange multipliers, and because of that, we get the saddle point problem. Okay, so there is a lot of theory, and this is very similar. Here, our pressure is a Lagrange multiplier enforcing the divergence constraint, the zero divergence constraint on the velocity. Okay, it is called a saddle point problem because of how the space looks like. So in terms of like when we actually if we take those functions, if we take a very simple example, okay, and if we look at that landscape, so the surface looks like a saddle. That is why it's called saddle point problem. So here, okay, in U we are minimizing. Okay, so we are looking at the minima, and in P we are looking at the maximum. So we have only one location at which the solution is stable. Okay, if you have any other points, for example this point, then they fall down, right? So if you drop a ball somewhere, okay, so it will fall down, right? So that, yeah, so that because of this inverse of stability, we cannot choose the elements arbitrarily for U and P, okay, as we discussed already. So the spaces should satisfy the inverse of condition, and it is this condition. Okay, so if you don't follow these conventions, so don't worry. Okay, you can learn if you want later by referring to the textbook that I suggest. Okay, so right, that's the theory. So if you want to keep this as it is without adding the stabilization, like when we add the stabilization, this non-zero will disappear. So we have this zero will disappear. We have a non-zero blot here. So we can solve it, and we get stable solution, that is pressure and velocity fields without spurious oscillations. But the alternative is to use LBB stable elements. Okay, the implementation is quite like little bit complicated. Okay, so in terms of LBB stable elements, we have quite a few combinations that we can use. Okay, so here, so this is called mini element. This is a 3-node element with a bubble, like qubit bubble. Okay, so which will be at the center. So what we basically do is take this bubble function from the P3 element and add it to the P1 element. Okay, so this combination of velocity pressure, that is P1 with qubit bubble and P1 for pressure, P1 with qubit bubble for velocity, P1 for pressure. This is a stable or inverse of stable combination. There are other combinations are P2 P1, P3 P2. Okay, these are with the continuous pressure, and we also have some other elements with discontinuous pressure. In this lesson we focus on the continuous pressure elements because they are a little bit easier to implement. Okay, this is for triangular elements, and for quadrilateral elements we have very similar combinations. So in terms of Taylor-Hood element, again we have this KQ and KQ minus 1. So for every order like for order k basis function for velocity, we take order k minus 1 basis function for pressure. Okay, for example, Q2, Q1, Q3, Q2. Okay, so for implementation, okay, so these are the textbooks I was referring to. Okay, if you want more details, these are some of the classic sources for mixed finite elements for incompressible flow problems. Okay, so for implementation, I'm going to focus on the quadrilateral element. Okay, but for the discussion, it is helpful if you also include the triangular element. Okay, so for a LBB stable elements, so like I said, so these are the Taylor-Hood elements. This is a triangular element, so 6 noded for velocity and 3 noded for pressure. This is a quadrilateral element, 9 noded for velocity and 4 noded for pressure. Okay, so velocity nodes, pressure nodes. Okay, now it becomes easier, like if you take mesh with the 9 node quad elements, and our first nodes, sorry, our pressure nodes will be the first 4 nodes because of the way we arrange them. Okay, so 1 2 3 4 5 6 7 8 9. Okay, because of the way we arrange them and because of the way we get the mesh information from Gmesh, so the first 4 nodes would be our pressure nodes. So by like that is also one of the reasons of using the standard image generator. So we get this mesh connectivity that we can use readily. Okay, so that means, so once we have the all the element node connectivity, we already have the element node connectivity for velocity as well as for pressure. Okay, we simply extract the first 4. For triangular elements, we simply extract the first 3. Okay, so again we denote or we represent our degrees of freedom as arrays. First, velocity degrees of freedom. If there are m nodes, we will have 2 by m velocity degrees of freedom, and if there are n pressure nodes, we have n pressure degrees of freedom. Okay, so our task is to compute the basis functions separately this time, because the basis functions would be different depending on the number of nodes, right? Okay, so here our task would be little bit complicated, just slightly, because our NP is no longer the same as NU. So because we are not using the same basis function for velocity and pressure, so we have to calculate NP separately. Okay, now I have already implemented this. Like I said, I would like to avoid mistakes, so I have implemented it already. I'm going to walk you through the code. Okay, so the previous files that I have written for the stabilized formulation, so I have renamed them with stabilized at the end. Okay, so stabilized, and then the stiffness matrix stabilized. Okay, first let's go through the stiffness matrix calculation. Okay, so this is the stiffness matrix. We pass the same data as before. Okay, we pass the coordinates, node numbers, viscosity, and body force term. Okay, and we get this plot, like each block of the stiffness matrix and then the force vectors. Okay, so this is the same as before. So we calculate the number of nodes per element for velocity. Okay, so this we can get from by sizing the node numbers that we pass to the function, and then depending upon the number of velocity nodes, okay, so we have this like control if condition. So if the number of velocity nodes are 6, then it is a triangular element, so the number of pressure nodes should be 3. Okay, so following this. Okay, and similarly, if the number of velocity nodes are 9, if the number is 9, then the pressure node should be 4. Okay, so using this we can implement for different elements. And then we have 2 degrees of freedom for velocity. We can calculate the size of the stiffness matrix, and then we get the coordinates of the nodes. Here, remember, we use again like velocity nodes, okay, because they also contain the pressure nodes. Okay, And since we are using a 9 node element, we need 9 RAS points. And you can also add like if condition here, and depending upon the like if the element is triangular or not, you can choose the DAS points appropriately. So if it is a triangular element, you can have another function like get DAS points triangle, and then pass the number of DAS points, and then it will give you the coordinates and weights. Okay, so you can implement it on your own. So afterwards, okay, so these are the major change that we need to do, the number of pressure nodes. Afterwards, this all these blocks they remain the same. Okay, so I still have GP. I just kept it there. Okay, if you don't use it, then we don't use it, or if you want, we can delete later. Okay, for now I keep it as it is, and then we loop over the draw points. We get the draw point coordinates. We we calculate the basis functions. Okay, so this step is the same as before. Okay, and here so I have added u. You can like it's up to you. You can add u or you may not add u. So just to differentiate. So okay, so now just to avoid confusion, I removed that u. Okay, so we did these basis functions. Okay, for the velocity DOF. Now here these are the basis functions for velocity DOF. That is why I have okay I had u. Okay, so let's go back. So okay, so what I'm going to do, we already have a variable nu. This is the basis function matrix for velocity, and so it becomes a little bit confusing. So that's what I'm going to do. I'm going to call this as NUU. Okay, this would be a vector of 9 noded like quadratic element basis functions, and then we create this matrix Nu for the two velocity components. Okay. Okay. So from this we get the vector, but we need a matrix. This Nu is a matrix, so that is why. So we have different variables Nu, Nu. Okay. So U is to denote that like this is for velocity. Okay. And when we calculate the area, okay, we use the velocity DOF, the space distribution for velocity DOF. Okay, that is we evaluate the integral. Okay, we evaluate our integrals over the 9 noded element. And then we need this NP, right? So basis function matrix for NP. NP, so P is a scalar, right? Okay, P is a scalar and NP is a 1 by N matrix. Okay, so when we call this function to calculate the basis functions, okay, so here we are calculating only the basis functions for 4 noded element. So here NP element pressure equal to 4. Okay, so from here, so we get the basis function for 4 noded element. Here it is 4 by 1 array, so I am transposing it to get here it is 1 by 4 array, so I am transposing it to get 4 by 1 array. Okay, so here this is the only difference, and we just change the names of these variables to distinguish them from P. Okay, afterwards everything else is the same. Okay, just that we need to change the names here. Okay, and in the stiffness matrix calculation, like they all remain the same. We just remove the contributions from the sorry. Okay, we remove the contributions from the stabilizations because we don't need the stabilization here. We can still use the stabilization, but we don't need it. Okay, so this is for the stiffness matrix. So there are like minimal changes. We just need first, the most important thing is we need to calculate the number of nodes for pressure space based on the number of nodes for velocity space. Once we do that, everything else is more or less the same. Okay, except that we need to calculate the basis functions for P separately. Okay, that is for the stiffness matrix. And in the main code, okay, main code, so from the beginning up to this point, it is the same except that we have to change the quads to quads 9 here because we are using the 9 noded element. And if you like in that case, so this mesh object consists of quads 9 like variable, and then we are using, since we are using the q2 q1 element, our okay, so this is not displacement, let me change. Okay, so our number of, again the same, like number of nodes per element for velocity is 9, number of nodes for per element for pressure is 4. Okay, so then we calculate the velocity DOF. So these are the this is the total number of velocity DOF. Okay, now the difficulty is it is in calculating the pressure DOF. How many pressure degrees of freedom or how many pressure degrees of freedom are there? So in order to do that, first let us look at the mesh. Okay, so this is the 10 by 10 mesh, and these are the node numbers. Okay, for the quadrilateral element, that you see, like these are the 9 nodes for this element. Now for this element, so we have 9 nodes: 1, 5, 81, 70, 14, 162, 163, 80, 164. Okay, now so our pressure nodes are the nodes at the element corners. Okay, so 1, 5, 6, 7, 8, and so on. And then 70, 81, 90, 99, 108, and so on. 69, 82, 91, 100, 109, and so on. Okay, so we need the nodes at the corners, not the midpoints or inside. So how can we get them? We can get them by extracting all the nodes, all the first 4 nodes from the connectivity matrix, and then we remove the duplicates. Okay, so in this way we get the nodes for the pressure space. Okay, what I say, so we extract all the, for all the elements we extract the first 4 node numbers, and then we flatten it, that, and then that is we get a like a vector or a array with okay, 1 row number of columns. Okay, and then we find the unit values. So this gives us all the pressure nodes. Okay, once we find all the unit node numbers, so we can add, so these are the pressure nodes and its size is the number of pressure nodes, the pressure degrees of freedom. Okay, so this is the only difference between the stabilized formulation and the LBB stable elements. In the stabilized formulation, our pressure DOF is equal to the number of nodes. Okay, the total number of nodes. Whereas in the LBB stable element, our pressure DOF are different because we use one order lower space. So first we get the all the pressure nodes in the mesh, and then we find the size, and then we have the total number of DOF. Okay, velocity DOF plus pressure. Okay, after that we create the connectivity matrices for velocity and pressure. For velocity it is the same except that we are using the 9 noded, so we have to change it to quads 9. For pressure, okay, for pressure it's a little bit tricky. So for what I am doing, I'm creating an array assembly for pressure. It is with like full mesh. Okay, all the nodes in the mesh, and then I initialize it to -1. Okay, and then I loop over all the pressure degrees of freedom. Okay, so that I access each entry in the pressure node. Okay, so these are our pressure nodes. So we need to know, like, for these pressure nodes 1, 5, 16 and so on, because like we need a continuity for these pressure nodes, right? So pressure node 1 DYF is pressure DYF is 1. This is the pressure node 2. So pressure DYF should be 2, but this is 5. So what we need to do is we need to create an array, this assembly for pressure for the whole mesh. Okay, for the whole mesh, where we create the degrees of freedom again for the pressure. Okay, so we already identified all the corner nodes. Then in the increase in order, we label them as pressure degrees of freedom. So in assembly for pressure, so for the first node, so 1, it will be DYF1. The second node would be 5, for example, let's say. Okay, so then at 5, at assembly pressure at 5, the pressure DYF would be 2. We are increasing the counter, so and so on. Okay, so this assembly per pressure that we can use to get the element DYF connectivity matrix per pressure. Okay, okay, that's another key difference in the LBB stable element. And then, like, getting the fixed nodes, finding the fixed DYF, it is the same. Okay, except that we are using the 3 node line elements, and then looping over all the boundary nodes on the top. Okay, on the top boundary, and assigning the HDYF. Okay, using the function expression that we have used. Okay, they are all the same. It's all the same. Then loop over elements, it is the same. It doesn't change anything. Okay, we are not changing anything. We want to keep the code changes to as minimum as possible. Okay, so everything else is the same, and then we can plot. Okay, so this is the solution with 10 by 10 mesh. Okay, as you can see, there are no oscillations. That is the pressure. Okay, and we can also plot velocity. So velocity also no oscillations. Okay, and if you look at the variables, okay, so element way of connectivity. So velocity, there is not much difference. So pressure, okay, so okay, as you can see, so 158170, okay, 158170 are the first node, 4 nodes of this element, right? So they have become 154140. Okay, so we have changed the number so that we have we have the continuous increments for pressure DOF. Otherwise, okay, otherwise, so for elements which have node number that exceeds the pressure DOF, then we don't have we don't have that degree of freedom. So it is impossible to compute. That is why we renumber the pressure DOF. Okay, and if we look at the double stiffness matrix for the non-zero entries, okay, so this is the stiffness matrix, and here this is the KUU block, and this is the KUP block, and this is the KPU block, and this is the KPP block. It is 0, so that is why it doesn't display any dots here. As you can see, KPP, so it's all zeros, but compared to the total size of the stiffness matrix, this is quite small. Okay, we can check the number. Okay, so velocity DYF are 882 and pressure DYF are only 121. Okay, so it's about like 8 times. Okay, I'm going to upload these codes to the drive, okay, that I already shared. Okay, so again the main differences are in preparing the pressure DYF. Okay, apart from that, everything I try to keep everything as the same. That is the loop over the elements and the stiffness matrix. Again, the main difference is in preparing the basis functions for pressure. Okay, so with that we conclude this lesson and study Stokes equations in 2 dimensions. Any questions, please post in the comments.